Good. Do you want me to start now or wait until 9:05? Okay, cool. So welcome everyone. Thanks for coming to the Hack MIT 2021 puzzle walkthrough. So basically tonight we're going to be talking about the hack puzzle and revealing the solutions. So first, there are a couple links here. We're also streaming this event on YouTube, so you can go watch there and, talk in the chat if you want. And if anyone has any questions, you can check out the Slido link to submit them. Okay, so just for people who don't know, the Hack MIT puzzle is like a yearly CTF style puzzle that we release every single year around July, August, and this year it'll run until September, so you can access it until then. This year, our big puzzle consisted of 5 smaller puzzles. If you attempt and solve them all, then you get auto admission to our event, which is this weekend. And for anyone who wants to see any reference material on previous puzzles, this link here is for our puzzle walkthrough from last year, where we basically did the same thing and ran through all of them. For people who want to check out the puzzle this year, it is located at my.hackwsb.net. And we also have a feedback form for anyone who attempted the puzzle and wants to tell us about their experience. And overall, the puzzle will be open until the end of September. So yeah. So this year we had 5 puzzles. The total number of people who attempted to solve it was 906, and 29 people solved it by our deadline. So yeah, thanks everyone for attempting it. And this is also for people who got halfway through and got stuck, and we'll be talking about that today. So the first kind of puzzle 0 was our entry point. This isn't officially part of the 5 puzzles, but we always hide our entrance puzzle link inside our splash landing page, which is hackmit.org. So this year, what you had to do, basically we hid a hint inside our FAQ, which was that there's too much light. The intended thing that this was supposed to lead you to was to click on the sun, which would take you to dark mode. But we actually had a bunch of lanterns on our site, and I think it threw a lot of people off, but because of all the extraneous light. But basically you have to click on the sun, which would take you to the dark mode version of our site, which is here. And once you were in dark mode, you had to scroll down to the bottom of the screen and click on our Twitter icon, which would usually link you to the Hack MIT Twitter, but instead you have this pop-up with a fake tweet box. And basically we had around, I think, 20 Elon Musk tweets stored, and every single time you clicked on the Twitter, it would just choose a random one, and you basically had to just figure this out and and complete the rest of the tweet, press the tweet button, and that was how you accessed our puzzle. So once you press tweet, the page will kind of change a little bit to show this at the top, and all you have to do is click on the rocket, and that will link you to the puzzle link. So yeah, that was our entry point. So if you haven't noticed already, the theme this year for our puzzle was Wall Street bets, stonks, and cryptocurrency kind of related stuff. Because of that, our command center or main puzzle base was our fake version of Wall Street bets. You can access it here, my.hackwallstreetbets. And basically we took a bunch of Reddit source code and recreated it here. You can scroll down on the page and you'll see a bunch of fake Reddit posts, and each post basically corresponds to one of the 5 puzzles. You can see the puzzle link inside the post, and by commenting on each puzzle post, you can also submit your answer, and then it'll automatically respond to tell you if you are correct or not. So that was basically how users accessed all 5 puzzles. Each one is released sequentially as you solve them. And yeah, I think that's it for our entry point and command center. Annie, are there any questions?
I do not think there are any questions on the Slido.
Okay.
So we can move on to puzzle 1 now. Okay, so
do you want to share screen, or?
Yeah, I'll start sharing my screen. let's do desktop. There we go. Okay, yeah, so the first puzzle is called Hack Cookie. It was made by one of our team members, Mafaro. It's like a little cookie clicker based game. And also at the start, there's a little password you have to crack to get to the second step of the puzzle, right? So usually in CTFs, if you ever see just like a password field on its own, right, and you have like almost no hints on like how to do it. Actually, there were a couple of hints in our puzzle Slack, so you should join that next year if you're ever interested. And one of the main hints was to like try out a SQL injection, right? Because if you just have a password field, this is usually like one of the only ways you can crack things like this, right? So I will go to my favorite resource, which is the wiki for SQL injections. And if we go here to the very first one, you can try it and we magically get in because if you look at our source code over here, we had an insecure SQL statement where we inserted whatever string you gave us into our SQL query to check if your password existed in our database. And this is like very bad practice, things that you don't actually do in real life, but we did for our puzzle. Fun fact, this actually broke several times and we had to go into our box and fix it a lot. Um, but yeah, so the main way you get past the first part of this puzzle is to use a SQL injection that exploits this query that's like fairly common, right? Okay, and then the second part of the puzzle is more self-explanatory, right? You've bypassed the system and now you have to get your counter all the way to 5,000. So you start clicking the cookie, right? It's cookie clicker. The buttons go up, the numbers go up by one every time you click. But obviously you don't want to like click this button 5,000 times to get to the next puzzle. So we're gonna try to find a better way to do this. I think like one of the first things you should always try with puzzles like this is to look at the code that's being run when when you click the button, right? And one of the easiest ways to do this is to just look at the event listeners, which you can do through inspect element as I'm showing you here. So if we go to the event listeners for this, we can see that actually this is not the correct event listener. Here we go. Okay, wait. Actually, there's several ways to do this puzzle. So we're gonna also look at, you can also look at your network. Um, and you can see that every time you click the cookie, you're basically sending this post request to our server. And you can also do this through your browser. So if I just repeatedly send this GET request over and over again, every time my counter will go up by one. And one way to automate this is through like the fetch API in your console. So you can do a simple for loop like this. If I want to, let's say, call this length 5,000 times, you can do something like just fetch this API endpoint that we call every time the cookie is clicked. We can fetch it 5,000 times, and this will increment the counter by 5,000, right? But this is also very slow because we have to send 5,000 requests. A smarter thing to do is to look at the format of this request and see like there's this parameter called cookies at the end, which if we change, it changes the number of cookies that we add to our counter. So if I just change this all the way up to 5,000, we've added 5,000 cookies to our counter instantly with like one request. So there's like obviously a bunch of ways to solve this puzzle, which is why I think it was pretty fun. And yeah, so yeah, there's like several ways to solve this. And as you can see, if we log in again, we should have 5,000 cookies or a little more, right? So yeah, this puzzle has been solved. And then if we click the cookie again in our console, we'll get the flag. So yeah, that's the first puzzle, and I'll hand it off to Hillary, who's going to do the second one.
Awesome, thanks, Annie. Just gonna demo the second puzzle. All right. Okay, so second puzzle, let me just go to the slide presentation slides. And here's a highlight of what I'm gonna go through. I'm gonna go through the motivation behind the puzzle, and maybe inside the demo, show you some specs of the puzzle and the potential solution to the puzzle. I'm not gonna solve the entire puzzle because it's pretty tedious as well. But I'm just gonna show you an algorithmic way of thinking about it. But yeah, the puzzle is called Beaver Street Hack. And basically it was inspired by just Elon Musk's tweet feed. I was reading an article basically about how I think for the previous months, Elon Musk has just been tweeting about Dogecoin, and whatever he does, it seems like if it's something that is kind of controversial or something that's kind of unique, somehow the stock price of Dogecoin seems to either go up or go down. And he sends out these tweets that are funny as well. So one of them was kind of like a hex tweet, and when people respond to it differently, like for instance, the founder of Dogecoin deciphered it into something like an ordinary hex and did present another reply. And simply, a lot of people just replied to it a little bit differently. Some replied random gibberish, and others like the next winning lottery numbers. And I guess this idea was like, love the concept of a decoded tweet. Can we have a little crypto tip in a decoded way? So for me, that was like, oh, okay, why not we model something which is after this guy's feed? And the idea was that we have two things essentially that we have a tweet feed basically, and we have some sort of header account which is called Just Dating Masks, and we have about 24 tweets in total, and all these are decrypted. Encrypted with 3 encryption types, basically. On the other hand, we have some sort of market that is running as well, which represents the market of this, fake currency that we call Beaver coin. And the goal of the puzzle was that you have to figure out how the feed relates to the market, and in the end, you have to use your wallet, the amount in your wallet, to buy the puzzle code, and that puzzle code will give you like the solution, the secret key that you need to go into the next puzzle. Right. So if you start off the puzzle, just bare bones, let me just use another, let's just say user 1. I guess you reach this page and essentially you have 0 Beaver coin, but you have 0.314 31 cents to start with. And 0.314 is just basically my room number and also pi. So yeah, I thought that was kind of like cool to add. And then going to the feed, you start off with the feed and you have bare encrypted tweets, and you have to figure out what each encryption type is. So right off the bat, you can essentially tell if you're familiar with cryptography or anything, you can tell when something has been encoded in some sort of manner. And the basic 2 easy ones coming off the bat were this one, which was a hex encoding, and this one, which was bake encoding. And you'd essentially have to decode everything. But I guess a lot of people, when they were decoding this, they were kind of like not having an idea of what the market would do at first. And the market, when you started like this, it's kind of like nothing. You're starting at 0.14 at this time as well. So if you just take, first of all, like the hex that is there, and then go to any cipher online. This was a Bacon cipher. And if you go to a hex or hexadecimal cipher, probably you get the tweet being translated to actually an actual text, which you just copy back and then place inside. And it should be able to give you like a check mark, whether whether your tweet is correct or not. As you can see in other puzzles like this one, for example, your tweet will be correct. And if your tweet is correct, you would notice that the market either moves up or moves down based on what the tweet says. And the main idea was also for you to be able to keep in memory or keep in mind what each tweet does. For instance, each tweet always maintains a certain effect on the market, and it can either be high or low. So what I mean is that you always have a current trading rate that you have, and the trading rate always starts out very low, and you have to increase this trading rate. And the only way that you can increase or decrease this trading rate is by correctly starting the tweet. So there are about as I mentioned, there are 24 tweets in total. 12 of those tweets increase the market, and then the other 12 decrease the market. But however, the caveat is that each encryption type that you have, because we have 3 encryption types, increases the market or decreases the market pretty differently. And I weighed them based on maybe the order of difficulty that I thought. As you can see, the Bacon and Hex ciphers are pretty kind of easy to think about, right? So each of them, I think, was about increasing the market price by 100% and I think 150% respectively. But there's this kind of encoding that is a little bit different, which is encapsulated in some sort of base 64 encoding. But however, it has a Buford algorithm to it. And the idea was that if you solve all the other encryption types, the A's, the Bacon ciphers, and also the Hex ciphers, you should be able to get about 16 tweets that are pretty unique. And the remaining 8, you would have to reset the puzzle and then get the other 8 based on maybe having your luck coming on. Like if, for instance, this tweet was encrypted as some other tweet or some other encryption type in the next reset of the puzzle, now you would have to kind of like you're obscured from solving like this puzzle, this encryption type, sorry. So what you had to do was look for clues inside the tweet text. And one of the clues for solving this third encryption type was about a chess grandmaster named Daniel Dubov. And essentially, everything was just basically, sometimes I want to play b3, but Beaver coin standing suggests that I play e4, chess things. Beaver coin, imagine chess things with Beaver coin. Imagine we had a Beaver chess world champion hail the Beaver. The secret key to the 4th algorithm is the name of the 28th ranked chess master in the world, spaces lower caps, right? That's one thing. Another, I think, another clue was something about me hiding the 3rd algorithm to solve the 3rd encryption inside the HTML. So basically, it was something about hiding it under the profile div. So essentially, the 3rd encryption type was just solved by going here. Now, let me just pull it up again. So if you go here and then you copy the GitHub link and then you go here to this algorithm that gives you the book Buford. So that's what I said. The key to the fort is for you to be able to find the grandmaster who's ranked 28 in the world. And all you had to do was find Daniil Dubov. And when you find Daniil Dubov, you kind of decrypt the text by putting in the key and you put in the text from the tweet, and then you're able to cipher out Daniil Dubov, the text that corresponds to the encrypted tweet. So after you've gotten all the data that you need, possibly out of all 24 tweets or even 16, I think that would have given you sufficient money to be able to solve the puzzle. So the idea was that once you reset the puzzle, it will ask you whether you want to reset the puzzle. You get a new encryption types for each tweet. But I called a bluff in that the first round, each tweet is kind of randomized. But then once you refresh and come back, the tweet will start on in the same order that they started in the beginning. So what I had to kind of confuse people in a way. But you understand that now that you've gotten all the encryption types and the market is either going up or going down, and you understand that metric, all you have to do is kind of buy stocks and sell stocks. So you really want to kind of 0.14, the rate is very high. And once you decrypt the tweets that decrease the market, you want to buy a very low price. So definitely you would buy, let's just say you have the wallet that's 0.314, you buy 0.2, and then it'll give you some Beaver coin. And once you buy at a very low rate, you need to also increase the market for you to buy at a very high rate. So sometimes you want to sell maybe at a very high rate. You can only sell the amount that you have. And then you see that your wallet was, at the end of the day, to buy the puzzle code, you needed $900. And once you buy the puzzle code, you get the puzzle key underneath here. A lot of people were asking about the betting component. but in the end, I'm not going to spend as much as in the betting component because it was not even necessary. Why? Because we charged a steep price. I think you can only gain. We charged a maximum of $60 on your bets, so you can only. And the puzzle key was now it costed $900. That should tell you something that okay, the bets are not gonna come. Bets are not gonna come easy. So in a way, you should ditch them. So I guess a lot of people wanted to know about bets and stuff, but it was kind of like not relevant as well. But yeah, in the end, you'd buy your puzzle code and then have your code here, and then you take it to the next round. I think that's all.
Cool. Thanks, Hillary. So for the third puzzle, we have Jack and Julia. Do you guys want to share screen?
Yes, I will share my screen. Hold on. All right. Let's not start on that slide. Okay. So, puzzle 3 is called Double Agent. And the basic idea behind this puzzle is that it is a machine learning puzzle involving steganography. Steganography is, I don't know exactly what the definition is, but it involves encoding a message in something else. Like you take a big system and you encode some message in it. I think this is commonly done with like images. Like if you have an image of something, you can encode a message in the pixels of the image by increasing or decreasing them by a certain amount, so that they create some sort of pattern that you can extract out of the image. But I haven't looked into this in a while. So Google steganography if you want to learn more. But basically, this puzzle takes advantage of the, oh, thanks. This is a link to the puzzle if you want to try it out. Basically, this puzzle takes advantage of the fact that a machine learning model is basically a series of matrices. So if you have a model, if you kind of dig into it a little bit and take off the hood, look under the hood, all you're going to get is a series of weights. And these weights are all matrices with different dimensions. And when an input goes through a machine learning model, it just gets modified according to the operations and weights of the layer, of each layer. So what we did in order to create this puzzle was we wanted to take these weights and create a function so that when the function is given a machine learning model, it reads in the weights, like each of the matrices in the model, and outputs a message. And so this was how the puzzle started. We gave you this function and you had to start out by understanding it. So let's take a look at this function. Okay, so here's the function called decode message from model, because that's what it does. So basically, this first line, if you're not familiar with Python, it's okay. I'll try to walk through this. So this first line creates an array of characters, and it does this for each parameter in model.parameters. So model.parameters is just a list of the weight matrices of this model. So param is just one matrix. And you can think of a matrix as just, two-dimensional, some number of rows by some number of columns, array of floats, floating point numbers. And for each weight matrix, basically we take the sum of all of the weights in that matrix and then round it to the nearest integer, and then basically convert it to some number. Like we mod 27 so that we can map all of the integers to the range of the alphabet plus a space. So that's basically what this first line does. We start with the list of weights in the model, and we take each weight matrix and convert it to a letter. I hope that makes sense. If it doesn't, please speak up in the chat or something. I'm happy to clarify if need be. But so basically you get out of this line and you go from having a weight matrix or a list of weight matrices to a list of letters. And then basically, or sorry, this is going to be a list of integers because ORDA is going to be like 60 or something, maybe 65. And you're just going to add whatever this is. And so this is going to take, this second line is going to take that list of integers and convert it to a list of letters. And then this last line, the return statement, is just going to convert it from an array to a string. That's all that this function does. It takes in a model and it outputs some message. And so the first key to understanding the solution to this puzzle really comes through understanding this function, because we could have functionally written the same puzzle with a lot of different versions of this function. The key insight is that the solution is very specific to this function. So now that we're past that, let's go to the next slide. Let's think about how machine learning models are usually trained. Usually, actually always, you're going to train them with respect to some loss function. The most common loss function for most models is this thing called cross entropy loss. And all that it does is it measures the difference between the predictions that the model is currently making and the target labels. And intuitively, this makes sense because usually you start off with a machine learning model where the weights are randomly initialized according to some distribution. And so the model starts off making these pretty random predictions. And so you can run inputs through the model and it'll output completely random outputs. And you want to measure the difference between those outputs that the model is giving you and the target labels, or what you would want it to output. And so you have a loss function that measures that difference. And then if you try to minimize that loss, it increases the accuracy because your model iteratively gets closer and closer and closer to making the right prediction. So this is generally how you're going to change the weights in a neural network. And so, you know, if you're thinking about how we can encode a message in the weights of the model, you might be thinking about how we can kind of hijack this process. Can we make a custom loss function? And so, yes, this is the intended solution. We want you to make a custom loss function that optimizes for 2 goals instead of just 1. So the first goal is going to be the same one as the one that I just said, the one that you're going to use in basically training any machine learning model. You're going to have one cross entropy loss that measures the difference between the current predictions that the model is making and the target labels. And the goal of this first loss is to increase the accuracy of your model, because we imposed a constraint on you that the downstream accuracy of the model that you submitted to us, it had to encode the right message, but it also could not get less than 82% accuracy. So, because the whole idea of the puzzle was like, you're passing a message through this model and you can't be detected because otherwise they'll like find you out for insider trading or something. So your model needs to be like accurate enough. So we still need to achieve this first goal with your cross entropy loss. And then you're going to have a second loss that measures the difference between the current weight sums and the target weight sums. So if we go back to this function, the current weight sums are going to be basically, you know, you're going to feed the current model as you're training into this function, not exactly, but more or less, and you're going to see what the sums of each matrix currently are, and you're going to compare that to what you want it to be in order to encode your target message. And then you can only have one loss when you're training a model, so you basically add these 2 losses together, and then you're going to want to find a good like coefficient or trade-off between these 2 losses, because if you make one of them way too large, it will dominate and you won't be able to achieve both goals at the same time. So that is the intended solution to this puzzle. For most cases, training the model with this custom loss function should be enough to complete the puzzle. I know we got a lot of people who messaged us asking about like hyperparameter tuning, changing the learning rate, batch size, whatever. You did not have to do that for this puzzle, although I think some of you did. We also had some puzzlers who came up with an alternative approach, which is totally valid for the scope of this puzzle. where usually you're going to train your machine learning model on a training set and then evaluate it on like a held out evaluation or validation set. And this is so that your model doesn't overfit. But because we told you that we're only evaluating the model on the validation set, one other solution to this puzzle would be to train it on the validation set and force the model to completely overfit. And so you get like a very high accuracy at the start, and then you kind of randomly perturb the weights so that it matches the message that you need. And the idea is if you start off at such a high accuracy because you train on the validation set, it shouldn't matter that you are kind of randomly changing the weights because your accuracy is already so high. So yeah, these are the two, I think, most popular solutions to this puzzle. And that's double agent. I'll hand it off to Justin with puzzle 4.
Cool. I am Justin with puzzle 4. So I'm going to share my screen. I'll just do the whole desktop. All right. Cool. So puzzle 4 is called Hack Crypto. It's in the name. It's a crypto puzzle. And basically for this puzzle, essentially it's a blockchain. And actually, I'll just go through it like you would see. The link is hackcrypto.wallstreetbets.net in your username. So when you click on this, when you access this puzzle, you'll see like a website for this new crypto exchange called HackFace, the best crypto exchange in the world. Premier crypto exchange for Hack Coin, which is our Hack MIT currency. There's an About Us page, which has nothing except this handy reset button to reset the puzzle when you need it. And then there's a white paper, which just opens this PDF of this kind of troll blockchain paper. And this was a red herring. There's actually nothing in here, but I'm glad that some people read it very meticulously. So that's the white paper. It was kind of just to throw people off a little bit. And then you'll see there's a donate page. And as you can see, if you donate $1 million and 333,000, basically will, as a reward, will provide you with a complimentary Hack MIT puzzle answer. So it's pretty clear how you're supposed to get the puzzle, but how do you reach $1 million? So now this last button is the download client. When you click that, it'll download the HackFace client. And so HackFace is a fully functioning blockchain. And I'm going to show you what the exchange looks like. So essentially, it's just a interface from the terminal, and we provide basically a HackCoin miner, which mines HackCoin periodically, and we give you an exchange. On the exchange, there are a lot of tools, such as you can view the blockchain. So here are all the transactions on the blockchain, and you can also check your status. So how many HackCoin you have, how many dollars you have on the blockchain, the current market price of HackCoin, and then you can buy and sell. Oh, well, you can, if you have money, you can buy. If you have HackCoin, you can sell your HackCoin, and each HackCoin goes for $2. And then you can view current transactions. And then you can see my latest transaction was added to the blockchain. And in addition to yourself, there are also other miners who will also be mining blocks called Phineas and Ferb. They are continuously mining blocks as well. So that's a basic overview of the HackFace exchange. So I'm going to quickly just do a very, very fast crash course on explaining the blockchain. If you solve this puzzle, this is not targeted to you. But if you haven't solved it and you're curious, I'm going to really quickly do a very high-level view of blockchain. But if you're curious about this topic, you should definitely read more about it because it's very, interesting and relevant to today. So essentially, a blockchain is made up of blocks, pretty standard, and each block is just essentially a container full of specific data. So that data, in this case, when you're talking about blockchain for a currency, that data is transactions. So different nodes on the blockchain, a node being just any user who's using the blockchain. So like if I'm just a random person who wants to put transactions on the blockchain, I'm called a node on this network. I can submit transactions to the blockchain. So say my name is Alice and I want to give Bob 20 HackCoin. I will put that transaction onto the blockchain. The transactions are going to be put on a queue, and all the transactions of anyone using the blockchain will be put on a queue. And then there will be blockchain miners who mine blocks. and those blocks will contain these transactions. So they will constantly pull the transaction queue and pull down transactions and put them in the blocks that they're mining. When a block is mined successfully, the transaction is contained inside, and basically the entire contents of the block is hashed. So if you're not familiar with hash functions, basically it's a function that transforms some data into a string, and that string changes in random ways if the data that was hashed changes. So because there's this hash of the data inside the block, if you change any data within the block, then the hash will change completely. And in addition, each block contains the hash of a previous block. So that way, if previous blocks data are changed, it will change the previous block hash, which will then change the most recent block hash. And you basically chain these blocks in a line, and they're linked together because each block contains the hash of a previous block behind it. And that way, if you change any data in the entire block, in the entire chain, basically every hash on the chain ahead of it will change, meaning it's very, very hard to cheat the system. It's very hard to change data in your favor because everyone will know about it, and it's very detectable. So that's a very quick overview of how the blockchain works. Again, you should definitely read up on it if you're interested. Another point on blockchain mining. So if anyone can mine a block, then blockchain, like cryptocurrency, would not be very valuable. But there's this concept called proof of work, which basically means that when you're mining a block, you have to put a lot of work into creating that block. So then it becomes valuable. You're basically artificially decreasing the supply. And so in this case, proof of work, a very common proof of work is just a brute force hashing problem. So basically you have to hash a number. You have to create a hash that's less than a certain threshold. And because hashing is random, you don't know exactly what data can hash to a number below that threshold. And so you basically have to brute force and try every combination of data basically to get that hash. And that's why it's very hard and takes a lot of effort. And that's why it qualifies as a good proof of work. And that is what you needed to do with the blockchain miner. So yeah, that was a very quick overview. If you have any questions, feel free to ask in the chat and I will try to answer. So I'm going to give I guess I already gave a demo of the HackFace client, but basically everything I just talked about that you have to do on the blockchain, you can do with the HackFace Exchange. So you can view the blockchain, you view your own wallet, you can buy Hackcoin with cash and sell Hackcoin. And as you buy and sell things, those transactions get added to a queue, and then any miners, you, Phineas, or Ferb, will generate those blocks, and then the blocks will contain the transactions. And the entire chain is a functioning blockchain. So you actually, if you go back and change anything, the hashes will all change and the blockchain will be rejected. So how do you exploit this functioning blockchain so that you can get $1 million? One way you can do it, and some people did this, is to brute force and just mine. If you mine very quickly, you're able to, you will be able to get to $1 million eventually. Each time you mine a block, you get a block reward of 10 Hackcoin. So, and each Hackcoin is worth 20. So eventually, if you mine enough Hackcoin, then you will get to $1 million worth of Hackcoin. But the problem is the puzzle resets every 2 hours, and it is set high enough, and the other players mine at a fast enough rate that it'll be hard for you. You have to really optimize the mining to get very quick before you can actually reach $1 million within 2 hours. So that was not the intended solution, although some people successfully did it that way. The intended solution is an observation that you had to make while you were playing around with the exchange. So the crucial observation is that say I have 43,000 Hackcoin. Also, I'm running the solution right now. That's why the Hackcoin is increasing. But say I have a 43,000 Hackcoin and I want to sell like 5 of them. So I sell 5 Hackcoin. Oh, wait, hold on. Okay. So say I want to sell 5 Hackcoin. That is on the transaction queue right now. What I notice is that the vendor who's taking my Hackcoin will send me $10 before the Hackcoin actually reaches the blockchain. And that's a crucial observation because when the transaction is still pending in the transaction queue, it's actually not verified yet. And this is the crucial exploit that you can use to basically cheat and get more money. So how does this work? Let me go back to my slide. The solution is called Affinity Attack. So if you're familiar with any blockchain exploits, Affinity Attack is one of the most like well-known blockchain attacks out there. And that's why most blockchain, most cryptocurrencies, when they encourage vendors to wait until at least the transaction hits 1 or 2 blocks on the blocks deep on the blockchain before you actually send the money. And this is for this specific reason. So how you conduct Affinity Attack is you have to create a second account. In this case, you just have to make a new public and private key. And this second account is what you'll use to transfer your HackCoin to. So you first create a transaction transferring all of your HackCoin to this dummy account. And then you mine a block with this transaction in it, but you don't put it on the blockchain yet. So you just hold this block ready. So you're basically ready to immediately send all your money away to this dummy account. Then you submit a second transaction buying a ton of HackCoin from the vendor. And this transaction will be submitted to the transaction queue. And say you spend all of your money you spend all your money selling HackCoin. That's a typo. And that will be added to the transaction queue. Once it's added to the transaction queue, you immediately put your pre-mined block onto the blockchain. So what the blockchain sees is that you have sent all of your HackCoin away to this dummy account. So when this transaction where you're selling HackCoin to the vendor hits the blockchain and somebody mines with it, it's going to be rejected because the blockchain thinks you have no more money. And but the fact that the vendor sends you the money before it's verified on blockchain means you still got all the dollars from the vendor without actually having to sell your coin. And then you just have your dummy account transfer all your HackCoin back. And so then you get a lot of cash money. So that was a little confusing, but I have an example. So say I have this dummy account. The dummy account's name is 55C82, whatever. And I have 15 coins. I transfer all 15 of my coins to this dummy account in this transaction, but I don't put this on the blockchain yet. Then I submit a transaction where I sell my 15 coins to the vendor. Right after that, I immediately put this transaction to my dummy account on the blockchain, and this pending transaction gets rejected. But what I end up with is 15 coins and $30 in cash. So after that, I can sell the 15 coins again and get $60. So I end up with double the value that I have before. And this is the solution because basically every time you mine a block successfully, you will double the amount of HackCoin you have instead of just getting 10. And that's how you reach $1 million. So that's a very long explanation, but it's a complicated process. My last slide is basically, there's a few other solutions that were viable. One is a brute force solution. The other was a remote code execution solution because we use JSON Pickle. In my opinion, those are all valid solutions. And the Easter egg is that the Phineas and Ferb's name is spelled Phineas because it's Affinity Attack. So I don't know if anyone actually caught on to that, but that was a hint. All right, that is it for Hack Crypto.
Wait, Justin, do you want to answer the question in the chat?
Oh, yeah. That was not the intended solution. I don't think that should work, but yeah, I'm down to check that later. I feel like there should be a check for that. But yeah, I mean, I'm happy to check it later. Yeah. There were a few times, because we allowed remote code execution as a solution, there were several times where, you know, the server code was changed. So that might have been like one of those times. But yeah.
Okay, great. Thanks, Justin. And the last puzzle is Annie's puzzle. So take it away.
I think Amanda's going to start for this one.
Yeah. Okay, sorry. There's a train that was just going by. I didn't know it was still going on, but now it should be fine. Yeah, okay, so I'm going to intro this last puzzle, which is primarily based on smart contracts, Ethereum, which is a type of cryptocurrency, and also using an algorithm to basically find the shortest moves to win a game. So this intro to this puzzle, which is at chadtomoon.hackwsb.net, basically actually demos a very small version of this game. So you can try out for yourself exactly how the game works and like what the mechanics are. So if I start this game, there are 3 moves that you can do, which is shoot with your up key in this case, or move left and right. And each time you do that, all of these monkeys will fall down and move down 1. And if any time that any of these hit the ground, and you'll lose a life. And you'll see that as I'm moving and as I move more, that some of these lives will fall away because some of these monkeys are hitting the floor. So if I go and solve this now, I might not get this on my first try, Lamel, because I don't know how to do this. But you can see that if you lose, that you can lose this game. But if you eventually solve it, then you can wait for it to reload, and then it'll take you to this next part that I guess Annie will explain.
Yeah, so as Amanda was saying, like the main point of the first part of the puzzle, oh, let me share my screen. The main point of the first part of the puzzle was to like share the mechanics of the game, right? And like the main 3 mechanics you get from the start are, after every move, each ape falls down 1 square. You can shoot to destroy an ape, and you can also move left and right, like Amanda said. And also you lose a life every time an ape falls to the ground. So in the next part of the puzzle, we're gonna like be taking all of these like principles to another level and like applying them to a much harder and larger puzzle that you probably won't be able to solve by hand. So yeah, okay. So the next part also adds a twist in the sense that, let me present, there we go. It also has a twist in the sense that we're also running this contract, we're running the puzzle as a smart contract instead of it being on your browser. So this adds like another layer of complexity, like another tool you have to learn to interact with the puzzle. So I'm going to start off with explaining the context. Smart contracts have a lot of context. So basically what they are is a piece of code running on the blockchain that you can interact with, similar to how you'd interact with an API on the web, right? So you can like send a GET request sort of and send a POST request to change things on a smart contract. So they're like a box on the blockchain that can send you data, and you can send it data to store and save and do whatever it wants with it, right? So some of the ways that smart contracts are interesting and like unique and different from normal APIs is that everything involving smart contracts is usually framed in terms of a transaction. This is because they're like built on top of blockchains, which are like completely based on transactions, right? And Ethereum is like the #1 smart contract platform right now. So this is what the puzzle used. And another interesting caveat is that for reading and writing data, they're actually very different problems on the blockchain. Writing data takes a lot of work on the miner's part. So you actually have to pay the miners whenever you want to edit data on your smart contract, but not the other way around. If you want to read some data from your smart contract, it's actually free. And this also shows up in the puzzle. Right now, obviously, this is like all very like loose and rough. We'll get more into it in the walkthrough, and it should become more concrete. Another important thing about smart contracts is gas. Gas is like a way to make sure one user can't like completely take down the entire Ethereum blockchain, right? You want to make sure no one smart contract is taking up a huge amount of computation power. And the way you limit that is by measuring the computation power. So every function, whether it's like adding 2 numbers or like storing an integer, costs some amount of gas on the Ethereum blockchain. And you have to pay real Ethereum, like actual money, to run these transactions in your smart contract. So the more work you do, the more money you will actually have to pay, right? So gas is a measure of like how much computation and storage power your function is using, and gas price is a measure of how much you're paying for each unit of gas, right? Also, this all recently changed with like a new Ethereum update. So like this is all very new stuff that's still changing. And then the way we interact with it in our puzzle is something called the Web3 API. This API is like basically a way to interact with smart contracts in your browser through JavaScript. It's mainly used to make it easier for end users. And yeah, so we can get into the Web3 API a little in our puzzle. So first, let's start off on a new browser so we can see what the puzzle will look like for a new user. So yeah, we open up our puzzle page and we're greeted with this Doge, my favorite character. And to start the puzzle, we have to get a new contract. This will open up your whatever wallet you have installed on your browser. And like I said before, each operation on the Ethereum blockchain costs money. So you need to like have a wallet with some Ethereum beforehand to even like participate in this puzzle, right? Because you need to be able to like read and write data, and that costs money, right? But in this case, we're using something called the Ropstein testnet, where you can get 5 Ethereum for free from like several different faucets. So you didn't actually have to spend any like real cash to do this puzzle because we were using a test network. The only downside of this is that test networks are usually a little bit slower and they're like more prone to getting DDoSed and stuff like this because everyone else can also get like lots of computation power for free, right? Okay, so if we click get new contract, we can just click confirm. Let me reload this. Okay, actually, I think I have to use my other browser because my Chrome is broken. Sorry about that. Okay, so now we can get a new contract. Close this. Okay, we're having slight technical difficulties. Okay, so in our console, let's see, we're getting a few bugs. It seems our puzzle is down. Okay. I think our actual puzzle for this has just gone down. So I will talk through the rest of it instead of walking through it. Okay. So essentially the puzzle was a smart contract where you played this game, you see with the little Chad and the apes falling down. The only difference between the actual puzzle, the browser version and the smart contract version was the smart contract version was slightly bigger. Instead of there being 5 columns, there was 12 columns and there were 6 rows, right? So the actual size of the board was bigger. So if you wanted to write a program to actually solve this puzzle, it would be much harder to brute force. As you see in this case, like you only actually need 12 moves to solve the puzzle. So if you wanted to write a program, you could just try like all 3 to the 12 possibilities for you have 3 options at every move, either right, left, or shoot. So you could just try to brute force all of these possibilities. And eventually you'd be able to solve like a small puzzle like this, right? The main like the third interesting part of this puzzle that you really had to think about was what algorithm do you need to use to solve this larger puzzle board, right? So in this case, there was actually like a lot of different solutions, which I think was nice, right? Um, the easiest solution was probably to just move all the way to the right and keep shooting whenever you see something above you, and then move all the way back left. This will be guaranteed to like destroy all the balloons. The only downside is that this may not always work because in some cases you'll actually die before you're able to kill all the balloons. So as you see in this case, right? If you move in the wrong direction at the start, you'll actually run out of lives and die before you're able to get to the other side. So like you have to like think about your moves carefully in this game in some cases, but also some board games that we gave were easier than others. So you're actually just able to move like right and left, and then you're just able to instantly solve the puzzle. The intended solution was to actually BFS through all possible board states, which is a slightly more complicated to code, but not significantly. The main idea for the BFS was for at every step to try your 3 possible moves, which is to move right, to move left, and to shoot. And then add the results of each of these moves to a queue, right? So we start off with our initial state, and then after our first iteration, we have 3 new boards, which are the result of moving right, moving left, and shooting. And then we pop the next board from our queue, and we repeat this process until eventually all of the gorillas falling on our board are gone, right? So the main thing you need to like make this algorithm better than brute force is a way to keep track of which boards you've already seen. And the easiest way to do this is to just convert your board, which is a 6 by 12 array, into a string and just put it into a hash map, right? So like if your board is all zeros or something, you just put it into a hash map. And then if you've already visited it, it takes O1 time to check that. So you can check that very quickly in your for loop every time you're testing out, you're popping a new move from your queue. So this will help us get rid of combinations that don't do anything. So for example, combinations like left, right, shoot are the same as the combination right, left, shoot. So this will like get rid of a lot of like the redundant possibilities and help you actually run the algorithm like within the allotted amount of time, which is 10 minutes for this puzzle, right? So yeah, that was the main solution for the last puzzle. And I think now we can take some of the general questions people had on Slido. So Nat, do you want to answer the one about infra and technical challenges?
Yeah, sure. If anyone if any of the people who made puzzles also have any answers, feel free to interject. But I think on the infra end, some main challenges were that first, like deploying like a puzzle that would be visited by like a couple hundred people in a short span of time was a little bit challenging. I think our server went down a few times in the first like 30 minutes. And I think also a lot of people came up with definitely like unintended solutions by exploiting like security vulnerabilities that we ourselves didn't notice, which also managed to bring the servers down a couple times, like the RC attacks in Puzzle 4. So I think dealing with those were some of the main challenges. But does anyone else have any challenges?
Yeah, I remember for puzzle one, I think the SQL injection was probably one of the more difficult puzzles to run. Obviously, since it was the first puzzle, it got the most traffic. I think like as Nat showed before, it was around 1,500 people who were attempting the first puzzle at the same time. And we didn't like code our SQL injection in the most safe way. So sometimes people ended up using injections that just broke the whole server, and we had to like restart it several times until we figured out like a safer way to do this exploit. So I think that was probably the hardest infra challenge we had with the puzzle. The infra challenges as you go like further along in the puzzles get slightly easier. Like at puzzle 5, I'm pretty sure only 50 people even attempted it, so we didn't have to worry about like the same issues as with puzzle 1 where there was like 1,500 people. And then there's another question about Hillary's puzzle. I don't know if Hillary has time to answer that. Actually, I think another good question is the one about what's something we'd recommend to beginners for solving hack puzzles. I think a good idea is if you're a beginner to try other puzzles similar to the Hack MIT one. Hack MIT's puzzle is like very similar to a CTF, but I'd say ours is a little harder because we only have 5 challenges and you have to do them all in order. So if you're a beginner, it's like very difficult and probably not feasible for you to solve all 5 puzzles on your first time. So like I wouldn't feel bad about this. So yeah, I'd recommend trying other CTFs with like a wider range of problems. So that way you can like build up your skill set and eventually be able to solve like all 5 of the Hack MIT puzzles. Nat, do you have any other remarks?
Yeah, I agree. I think it's definitely harder for beginners to like solve all 5, but usually the first and second ones are they like kind of increase in order of difficulty, and a lot of our puzzles are based off of like kind of like more commonly known ones. Like SQL injection is a really like common puzzle to run into. So if you're a beginner, I definitely just say like look up resources related to like CTF and try those. And you can also read our puzzle like walkthrough blogs and videos, I think going back to like 2018 to like see, because we often like HackFace, the Hack Crypto, also showed up like a couple years ago. So I think that would help.
Yeah, I think that's all the time we have for the puzzle walkthrough. Thanks to everyone for showing up. It was nice seeing so many people here. I hope you guys enjoyed it. And yeah, thank you.